Welcome to T3, Day 3 of Calculus. Today we're going to make n get really, really big, meaning the number of subintervals is going to grow and grow and grow and grow. What we learned was that we could make our guesses for the area under curves. The area under curves, we can make those guesses more and more accurate by increasing n in value. So what we're going to do is first introduce some new notation here. So as n gets really, really big, that little e sign right here, this means sigma, the sum of. So as n gets big, the sum of the area of the rectangles approaches the actual area under the curve. You can think of this as the actual area under the curve, and the curve is f of x, from A to B. So as n gets bigger and bigger, the sum of the rectangles gets infinitely close to the actual area under the curve, which is this right here. This is the actual area under the curve from A to B. And the way you say that out loud is we say that this is the integral of f of x from x equals a to x equals b. The integral of f of x from x equals a to x equals b. That is the actual area under the curve. So in example 3 here, we're going to evaluate the area under the curve, and that's the curve x squared from 0 to 2, which you state as the integral from 0 to 2 of 0 to 2 of x squared. And we're going to do it by hand. We're going to go from 0 to 2. So we're starting at 0 and we're going to 2. Notationally, this is the a value and that's the b value right there. So now we know that n is equal to 4, and we can find the delta x, meaning the gap to the next one. You can do that by doing 2 minus 0 over 4. So it's going to be 2 over 4. So we know the gap between each two is a half. So the next one will be a half, and then you add a half to that, you get 1, and then you get 3 halves. Now to fill in the other pieces, all we're doing is squaring each x value. So it's going to be 0 squared, it's going to be 1/2 squared, which is 1/4, and this is going to be 1 squared, which is 1, and 3 over 2 squared, which is 9 over 4, and 2 squared, which is 4. So we're going to do a Riemann sum on our calculator. We're going to do left and right hand. Now we're going to use a calculator, but we don't really have to on this one because you should be able to do this by hand. And we do the left values are going to be 0 squared, 1/4, 1, and 9 over 4. So we know the delta, the gap between each x value, the delta x is a half. So for the left here, we know it's going to be a half times 0 plus 1/4 plus 1 plus 9 over 4. And for the right, we know it's going to be 1/2, and the right-hand ones will be 1/4 plus 1 plus 9 over 4 plus 4. And when you add all those up, you end up with 7 over 4 for your left estimate and 15 over 4. So if you wanted a good estimate, you could average the two. The average of the two is 11 over 2. So our guess is 11 over 2 using 4 subintervals. Now we could use more subintervals to get a better estimate. So let's say we wanted to do this one. We're going to evaluate the area under the curve, the integral of x cubed from 0 to 3. Now we could make a table, so let's do that. So now we have our table, and we found that by writing in our first x value right here and ending with 3. And then we found the delta by doing 3 minus 0 over 5. So it's 3/5, then 6/5, then 9/5, then 12/5, then 3. So now we need to fill in the bottom half of the table, and that's going to be done by cubing each of these. So it's 0 cubed, 3 over 5 cubed, then you end up with our filled in table. So now we can do the same exact thing we did before and write out the left and right estimate, left and right hand estimates. So we know the gap is 3/5 in each case, so it's the same on each of these. And now we just have to write out all those fractions starting at the right place. So the one on the left starts with 3, and the one on the right starts with 3 over 5 cubed. So if we write this out, you end up with these big fractions, and then you need a calculator to do that out. Please use a calculator. You end up with 12.96 for your left-hand estimate, and you end up with 29.16, and then you can do the average. You could do the average, and the average in this case will come out to be 21.06. So I could ask you to do n equals 100. You do the exact same thing, but this would keep on going. Now, is that something you want to do by hand? No. Instead, you're going to use an applet, which I've given you a link to at the top of this page. Here's what the applet looks like. So I did the two cases, well, the first of the two cases we did before, which is x cubed, going from 0 to 3, 5 rectangles left, and we ended up, oh look, 12.96. So let's change it to the right, and you can replot it. This will be the overestimate. Oh look, 29.16. So now we can use it to do 100. rectangles. Let's do the left one first. We plot this and we end up with, ooh, it's really, really dense under there, 19.847. And let's change it to the right and you end up with 20.657. So this is a great way to do it using your, quote, calculator, in this case, your surface. So if you average the two, you end up with 20.252. So that's our new guess. So let's now use the program to do this integral right here. So let's use the Riemann program on our surface and let n equals 4. So it's the square root of 1 minus x squared from -1 to 1. So I used the applet and went from -1 to 1 using 4 intervals. And here's the left-handed one, and here's the right-handed one. And you'll notice that in this case, it came out to 1.366366. You can see that decimal underneath right here. And on this one, it came to 1.36603. It actually came out to be the same in both, which is possible. And it also gives you the actual area right there, 1.5708. And you can get a better estimate. If you want to get an estimate for the area, you can just crank it up to 100, which is what I did right there. And in this case, the estimate was 1.569. This applet also gives you the actual area, which is super helpful, 1.5708, same thing as before. So the more rectangles, the more accurate your guess. Evaluate the integral from 1 to 3 of x squared to within 1 decimal place of accuracy. What is the smallest n value needed to achieve this degree of accuracy? So as n gets bigger, the guess gets better and better. So how high, how big does n need to be? How high does n need to go in order to make sure you're within 1 decimal place? So the first thing to remember is the error is f of b minus f of a times delta t. In this case, that's what our error is. That's the definition for error when we're doing these estimates. 1 decimal place is 0.1, so we want it to be 0.1, and a and b, so that's your b value and your a value. So f of b is going to be 3 squared, and f of a is going to be 1 squared delta t. So when you do this out, 0.1 is equal to 9 minus 1 delta t. So therefore 0.1 is equal to 8 delta t. So what does that mean? Delta t is equal to 0.1 over 8, which is 1/80th. So we know that delta t has to be 1/80th. Well, we also know that n, the number of intervals, is equal to b minus a over delta t. So now we know that b is 3, we know a is 1, and we know delta t is 1/80th right here. We took that and put it right there. So now what do we end up with? 2 over 1/80th, which is 2 times 80 over 1, which is indeed 1/60th. So if we wanted to actually make that estimate, we'd have to make n be at least 160. N needs to be at least 160 for our guess to be within 0.1. If you wanted to, you could put that into the applet and see what our guess would actually be. So let's do that. So I just used the right hand on this, and I did 160 intervals, and you'll notice that our guess on this one is 8.7162, and the actual is 8.66667, and that is within 0.01. It is within 0.01. Awesome. You can test that by just doing 8.7162 minus 8.6667, and that will be less than 0.1. So let's do another one just like the one we did before. So we have the integral from 2 to 8 of 1/2 to the x, and we want it within 2 decimal places. So that's 0.01 in this case. And we know that that has to be equal to f of b minus f of a. So that's going to be 1/2 to the 8th minus 1/2 to the square times delta t. So no, delta t is therefore going to be 0.01 over this decimal place. It's going to be 1/2 to the 8th minus 1/2 squared. And if you do that out, you know what delta t is equal to 0.041. So now we want to find the n value, and that's b minus a over delta t. So we're going to plug that in right there. So n is equal to 8 minus 2, that's b minus a over 0.041. So n is equal to 147.6. And you want to round up because you need it to be great. N has to be a whole number, and it has to get you within. So you want it to be 1 greater than this. So you round up. So it's 148. You want n to be 100. So on 8 here, it says write an integral expression that represents the area between those two graphs. So if we want the area between the two graphs, let's do the area under the first one and then subtract the area under the second one. And this first one is higher always on our interval because x squared plus 4 is going to be greater than x plus 2 from 2 to 4. So we do the integral from 2 to 4 of the first one, like this, and then we subtract the integral from 2 to 4 of the second one, like this. That's what we want. And just here's one bonus integral rule. You can glue these together, and you go from 2 to 4 of the first one, like this, minus the second one. You can glue them together. It is allowable. And the way we do this is it wants us to estimate it using n equals 20. So if we simplify this a little bit, we can simplify the polynomial. We have x squared right there, and then we're subtracting x right there, and then 4 minus 2 is going to be plus 2. We want n is equal to 20. So let's use applet to calculate that. First I plotted it using the right hand from n, right side with n is equal to 20. We did right and left hand. We have our estimated 17.17 and estimate is 16.17. And when you average them, you do 17.17 plus 16.17 over 2. End up with 16.67. And then this actually tells you the actual, which is 16.6667. When you see that, it is okay to infer that that is 16 2/3. So